Kia ora, Robert McLaughlin here again. Welcome to 162.04, week 8, actually lecture 3. There's a typo already, that's not too good. Lecture 3, continuing the study of constant coefficient linear systems. We'll finish today, we will do two things. We'll finish looking at repeated roots, repeated eigenvalues, and we will also look at complex eigenvalues. We saw last time that if you have a repeated eigenvalue, it may happen that that eigenvalue has a lot of linearly independent eigenvectors to go with it, in which case you can find the general solution that way. So now we want to do the case when you don't have a full set of linearly independent eigenvalues. So that's when the geometric multiplicity, the dimension of the null space of A minus lambda I, is less than the algebraic multiplicity, which is the number of times that eigenvalue occurs. I'll just do the first case that arises here, which is where I just need to look for one new linearly independent solution. The general case where you need more solutions is not very different. So, do you remember what happened when we did the case of repeated roots for the second order linear systems? Instead of e to the lambda t, the new solution looked like t e to the lambda t. So that's not really rocket science to guess that the same thing might happen here, and it does. But the trial solution we need, turns out that you need two parts to it. You need an e to the lambda t times some vector, k, which is to be determined, and you need t e to the lambda t times another vector p, which is also to be determined. You need both those parts, and the k and p will point in different directions. We're going to substitute this into the differential equation, which was x prime equals ax. So that means I need to differentiate this with respect to t. And I get lambda e to the lambda t times k from the first term. And in the second term, I will get two terms differentiating t e to the lambda t with the product rule. I will get t times lambda e to the lambda t plus derivative of the first term times the second term, e to the lambda t, all times the vector p. And this is supposed to equal ax, which itself is equal to a times e to the lambda t k plus t e to the lambda t p. So this has to equal this for all t, which means that the like terms must be equal. So I need to compare like terms. If I look at all the coefficients of e to the lambda t, so without the t's in it, what do I get? Well, I get one of those here, and that has to be equal on this side to this one and this one. They all have e to the lambda t times a vector, not depending on t. So that gives me a times k is equal to lambda k plus p. And if I do what I did earlier, when I had the ax equals lambda x, I move the lambdas to the left hand side, and I get a minus lambda I times k is equal to p. Next I look at the terms with t e to the lambda t in them. Here's a t e to the lambda t. Here's a t e to the lambda t. So I get a times p is equal to lambda p. Do the same thing again. I get a minus lambda I times p equals 0. Now remember, I know lambda already. That's the eigenvalue that I'm considering. The unknowns here are k and p. Two vectors to determine, two vector equations. The second one doesn't have a k in it. In fact, that is just the eigenvector equation. So that means p is an eigenvector corresponding to lambda, which we would have worked out already. So we can say that we know what P is. Then we substitute P into the first equation and solve A minus lambda I times K equals P. Now, A minus lambda I is a non-invertible matrix. So if you just tried to solve A minus lambda I times K equals P, in general, that equation would have no solutions. But if it does have a solution, then you found your second linearly independent solution. And it will be the case that when you're doing this case where the geometric multiplicity is less than the algebraic multiplicity, then this equation will always have a solution. So you don't need to go through this derivation every time, but you do need to remember what the solutions look like, and you do need to be able to solve these two equations in a particular example, which is what we'll do next. So here is an example, 2 by 2 case, which has been carefully chosen exactly to illustrate this phenomenon. So here we go. First we work out the eigenvalues. I need to compute determinant of A minus lambda I. That is the determinant of 2 minus lambda 4 minus 1 6 minus lambda. That is 2 minus lambda times 6 minus lambda minus 1 times 4, which is lambda squared minus 8 lambda plus 12 on the left plus 4 on the right makes plus 16. I factor it. It's lambda minus 4 squared. That is equal to 0 when lambda is 4 and 4. So I have a double eigenvalue at 4. Now I need to find the eigenvectors. A minus lambda I is equal to, substitute lambda equals 4. 2 minus 4 is negative 2. 4, negative 1, 2. Notice that the second row is a multiple of the first, so when I row reduce it, I get negative 2, 4, 0, 0, as expected. Negative 2k1 plus 4k2 equals 0. I can choose k2 equal anything. Let's make it 1. That means k1 is 2. And the eigenvector is 2, 1. So there's only one linearly independent eigenvector. If I'd chosen a different k2, I would have just got a multiple of that eigenvector. So my geometric multiplicity is 1 eigenvector. My algebraic multiplicity is 2. So to find the second solution, I need to solve pen is malfunctioning. A minus lambda I. Remember that equation from before? A minus lambda I times K equals P, where P is the eigenvalue. 2, 1. In other words, I'm solving the same matrix I worked with before, negative 2, 4, negative 1, 2, times K is equal to 2, 1. Again, notice that the second row, negative 1k1 plus 2k2 equals 1, is a multiple of the first row. I can ignore it. So I only have to work with the, in this case, let's take the second equation, minus k1 plus 2k2 equals 1. Now I only need one solution because I know once I've found one solution, I will know how to find the general solution of the differential equation. So I'll take, for example, k2 equals 1, substitute that in, and I get k1 is 2k2 minus 1, it's also 1. Put them all together, and I get, remember what solution I was going for? Here it was here. e to the lambda t times k, which I've just found. Lambda was 4. 1 plus t e to the lambda t times the eigenvector is a solution. I also know the general solution. It's a linear combination of the two solutions I've found. So any constant times e to the 4t times the eigenvector, 2, 1, plus another arbitrary multiple of the second solution, which has two parts, e to the 4t, 1, 1, plus t e to the 4t, 2, 1. So in this case, the solutions are not exponentials. In this case, it's where lambda is positive, it's actually growing faster than exponential, like t e to the 4t, and for long times, that second final term there would dominate. Okay, the final topic we want to look at is complex eigenvalues. And although I've mostly done small examples, these do cover all possible bases of what can happen when you're solving linear systems of any size. Well, I'll do an example later of finding the complex eigenvalues and eigenvectors, but suppose we've found them already. When the matrix is real, the eigenvalues and eigenvectors will always come in complex conjugate pairs. So I know that x, which is e to the alpha plus I beta t times a plus ib, for example, to take the plus sign, is a solution. Let's expand that out. That is e to the alpha t times e to the I beta t, which I can use Euler's formula, cos beta t plus I sine beta t, times a plus ib. Remember how to multiply complex numbers. The e to the alpha t is just out in front. I get, for the real part, cos beta t times a minus sine beta t times b, and for the imaginary part, sine beta t times a plus cos beta t times b. It looks a bit complicated, but it's not too bad really, because what's going on now is I've found a complex solution, but I know that the complex conjugate of this would also be a solution. So by taking those two solutions and adding them together, I would cancel out the imaginary part, and I would get that the two, what is happening? Fundamental solution set is e to the alpha t times this one, is one fundamental solution, and the second one also grows at the same, or decays at the same exponential rate, but has sine beta t times a plus cos beta t times b. So qualitatively, these solutions, they both grow or decay. They grow if alpha is positive, and they decay to 0 if alpha is negative. They both oscillate with the same frequency, beta. It's just that their directions are different. You get different combinations of these two directions, A and B, in the two different solutions. So these two solutions form a fundamental solution set. Okay, so let's do an example of finding the solution of a linear system with complex eigenvalues. Here's a 2 by 2 linear system. So the first step is to find the eigenvalues and eigenvectors. So here we go. First we have to find the determinant of a minus lambda I. That's the determinant of 1 minus lambda 1 minus 2 minus 1 minus lambda. Expand the determinant, I get 1 minus lambda minus 1 minus lambda minus 2 times 1 is minus 2. Simplify that, that is lambda squared plus lambda here minus lambda here, minus 1 plus 2 makes plus 1. Equals 0 when lambda squared is negative 1, or lambda equals plus or minus I. So I'm in the case when I have pure imaginary eigenvalues. In other words, the eigenvalue alpha plus or minus I beta. It's plus or minus I. So the alpha, the real part, is 0, and beta, the imaginary part, is 1. Now I need to find the eigenvectors, and I only have to do that for one eigenvalue, because they will always come in complex conjugate pairs. So I'll choose lambda equals I. A minus lambda I is 1 minus I, 1, minus 2, minus 1 minus I. Now, normally you would have to row reduce this matrix to find the null space, which is the eigenspace, and that would have to be done with complex arithmetic, which is a little bit tricky. So I can do a shortcut here, because I know that lambda has been chosen to make this matrix singular, so there's guaranteed to be a 0 row at the end after I've row reduced. So I really only need to work with one row, and I'll use the first row. So its equation is 1 minus I times k1 plus 1 times k2 is equal to 0. Now I do a second simplification, which is to say that I don't need the general solution. I don't need to set, for example, k2 to be an arbitrary parameter. So I'll just choose k1 to be a convenient number, and I'll make it be 1. That means k2 would be equal to minus 1 minus I k1, which is minus 1 plus I. So the eigenvector is 1 minus 1 plus I. So I found the eigenvalue and I found the eigenvector. I don't need to find the other eigenvector because I know it'll be the complex conjugate of this one. Now I can just use the result from the previous page to write down the general solution. Or I could do one more step. I could take this and split it apart into its real part and its imaginary part, 0, 1. Now I can write the general solution to the differential equation. It's going to be x, vector x as a function of t is going to be c1 times the first solution, which is going to be cos beta t, so beta is just 1, so that's cos t times the real part, 1, negative 1, minus sin t times the imaginary part, plus c2 times the second solution, which is sin t times the real part, plus cos t times the imaginary part. And you could write that out again by adding up those vectors and so on, but this is a very convenient and straightforward way to write the general solution.